Okay, so today we have Hongliang Jiang, who will tell us about modularity in Argyres-Douglas theories with A equal to C. Take it away.
Okay, so first of all, I need to thank the organizer for giving me the chance to speak here at the Quiver Meeting. So today I would like to talk about modularity in Argyres-Douglas series with A equals to C. So this talk is based on this paper. Let me first give you the outline of my talk today. So first of all, I would introduce the series that I'm going to study today, which is denoted as the TP-N Argyres-Douglas series. So there's a very important feature for this family of theory that the two central charges are the same. Then I will derive a very simple closed form expression for the Schur index for this family of theory. And I will then further study the modularity associated to this Schur index. Namely, I will show that it satisfies some modular linear differential equation. And using the modularity, I will study the high temperature behavior of Schur index. And finally, I will conclude. So first, let me introduce the theory to you. Before that, I would like to introduce another set of theory, which is called the DPSUN theory. So this family of theory is labeled by two integers, p and n, which are bigger than 1. And they are further satisfied subject to another condition that p and n are coprime. So this is important to make sure that the flavor symmetry is SUN. If this condition is violated, then the flavor symmetry may be larger. So in this case, the DPSUN theory is just a generalized Argyres-Douglas theory in the sense that the Coulomb-Brownian spectrum may be functional. Therefore, there's no direct Lagrangian realization for this family of theory in terms of n equals 2 supersymmetry. However, there are many other realizations. For example, we can realize through class S. So one can compactify the 60 0,2 superconformal field theory of type A m-1 on the Riemann surface with the irregular puncture and the full regular puncture. So the full regular puncture gives rise to the SUN flavor symmetry. And if we impose this kind of coprime condition, the irregular puncture would not contribute any further flavor symmetry. As a result, the final flavor symmetry is just SUN, or more precisely, PSUN. So since we have flavor symmetry, then it's natural to ask what would happen if we gauge the flavor symmetry. So we can take a collection of DPSUN theory and then gauge the diagonal flavor symmetry SUN. Then we can look at the one-loop beta function. It turns out the one-loop beta function is proportional to this quantity. So here I have this 2 times n from the vector multiple contribution and the sum of BI, which is a contribution from the individual building blocks. So in the end, one would find that the one-loop beta function is proportional to 2 minus sum of y, pi minus 1 divided by pi. So now we want to impose another condition that b equals 0 because we want to make sure that the gauge is conformal and the gauge coupling is a marginal deformation. So we can try to find the solutions for this equation. So obviously there are many solutions. For example, one can consider 4 copies of D2SUN. Then one can see that 2 minus 1 divided by 2 times 4 is 0. So in this case, we get b equals 0, and the corresponding superconformal field theory is denoted as T2, n. We can also consider the case that we have 3 copies of D3SUN. Then we can check this equation again. It's 2 minus 2 divided by 3 times 3, which is 0 again. And this gives another series of superconformal field theory, and is denoted as T3, n. There are also 2 other solutions. One of them is given by 1 copy of D2SUN and 2 copies of D4SUN. In this case, B is 0 again, and the corresponding superconformal field theory is denoted as T4, n. And finally, we can just take 3 DPSUN series, 1 D2SUN, 1 D3SUN, and 1 D6SUN. And B is 0 in this case again, and then we get a superconformal field theory denoted as T6, n. So in total, we see that we can get a family of superconformal field theory, which is denoted as TP, n, where P can take 4 values, 2, 3, 4, 6, and n can be 2, 3, 4, etc. but they are subject to a further condition that P and N are co-prime to make sure that the building block has only SUN flavor symmetry. So this is a theory that I'm going to study today. For example, we can illustrate the four series of theories in terms of this kind of diagrams. For example, in T2, comma N. Yeah.
Yeah. So what happens if you don't, if you relax this condition of coprime? So the symmetry is no longer SUN, you said?
Yeah, it's larger.
But it's still a fine theory, conformal theory?
Yeah, DPSUN itself is always superconformal, yeah.
Mm-hmm. Okay. And what is the symmetry in this case? That
it depends on the value of P. So if it's not co-prime.
You need to divide by the GCD. So it's SUN divided by GCD?
No, I think it's very complicated. It depends on the value of P, the relation between P and N. So I don't think there's a very simple formula. I mean, a way to say it. Yeah, but
Okay.
there's a formula to say it.
Okay, thank you.
Yeah, for example, for this T2 command, we just take 4 copies of D2 SUN, then we add this vector matrix, then we get the flavor symmetry. And similarly for the T3 command, T4 command, and the T6 command. So why do I care about this kind of theory? One reason is that this family of theory is very similar to N equals 4 superior Mean theory. One important similarity is that some of the two central charges are the same, namely A equals to C for the T become N series that I'm going to study today. More precisely, the two central charges are given by 1 minus 1 over P times N squared minus 1. So this is the important formula that I will use later. So it's also similar to N equals 4 because N equals 4 superior Mean is also proportional to N squared minus 1. So the difference is just this kind of factor 1 minus 1 over P. So now let me give you another realization of this family of theory using type 2B string theory. So we can consider type 2B string theory compactified on some isolated hypersurface singularity, which is a Casimir threefold defined in terms of a quasi-homogeneous polynomial in C4. So the type 2B realization is possible only for 3 series of theories, namely T3 command, T4 command, and T6 command. There's no type 2B realization for T2 command. For example, if we consider T3 command, then we can just compactify type 2B string theory on the isolated hypersurface singularity defined here, x cubed plus y cubed plus z cubed plus wn equals 0. Then we just get the T3 command theory. And similarly for the T4 and T6 command. So the corresponding IHS is given here. So the type 2B realization is very useful. For example, we can easily compute the branch spectrum from the deformation of isolated hypersurface singularity. Also, we can find the dimension of Higgs branch by resolve the singularity of IHS. And finally, it's worth mentioning that there's a more general family of superconformal field theories with A equals C, as studied by Khan, Rory, and Song, and they label this family of theory as gamma hat G. So in their notation, my T2 command is just the D4 hat SUN, and T6 command is just E6 hat SUN, and similarly for T4 command, T6 command in terms of E6 hat, E7 hat, and E8 hat. So here G is always the SUN, but more generally one can consider SO, 2N, or some E-type Lie group. So yeah, there's a question.
Hi, yeah, just because it's also related to Ami's question as well. When you have the G as SUN, generally speaking, it's actually not an A equals C SCFT. Again, you need the N coprime condition. So we actually defined the whole family, including the cases where they're not A equals C and you don't have the coprime condition. But for example, you need the coprime condition on N and now either some root of D4, E6, E7, E8 for this to hold. Yeah, I just wanted to just.
Yeah. The A equals 2 condition only appears when the coprime condition is satisfied. Yeah. Yeah, there's another question or comment?
Hi, I also want to make a comment that just the P and N coprime condition is specifically for SUN. You can also consider generic G, and it just means that then the P and the HG check are coprime, and that just gives rise to all the families of A equals C theories.
Yeah.
Also, if you did not have this condition given at all, you will not have the similarity with N equals 4 super Young-Mills in your earlier formula as well.
Yeah, I agree. Yeah. Yeah, but today I would only focus on this 4 series of series here listed in this table. So now I would like to derive a closed simple form expression for the Schur index for this family of theory. So as I said, so the TP N theory shares similarity with N equals 4 superMs. And one similarity is that the two center charges are the same. Another similarity is that somehow there's a very intimate index relation relating these two series. So that's something I'm going to talk about today. So let's look at the Schur index. So in general, for any for the N equals 2 superconformal field theory, we can consider the superconformal index. And first of all, one can consider specific limit. And one of the interesting limit is the Schur limit, where you get the Schur index. So the Schur index gets contribution only from the Schur multiplet. So this is the definition of the Schur index. As usual, we have the trace over the Hilbert space. Then we have this -1 to the f. So f is a Fermi number. Then we have some fugacity q to the e minus r's power. So e is just the scalar dimension of the local operator, and r is just the SU to r charge. So in many cases, the superconformal field theory has flavor symmetry. So we can also add the flavor fugacity xj here to the fj. So fj is just the generators. So this gives the definition of Schur index as usual. So for gauge theory with Lagrangian realization, so it's easy to compute the index just from the building blocks. For example, we can consider Schur index of N equals 4 to be a Mears theory. And we can regard N equals 4 to be a Mears theory as N equals 2 theory with one vector multiplet and one hypermultiplet in the adjoint representation. Then the Schur index can be easily found. We can just take the index of vector multiplet and index of hypermultiplet. Then we perform the Haar measure integration in order to project the gauge invariant sector. So here, this X is S for SUN flavor symmetry before gauging, and Y is for the SU2 flavor symmetry, because the R symmetry of N equals 4 so Mears is SU4R. So it becomes SU2R times U1R times SU2 flavor symmetry. So the first two factors is just the R symmetry of N equals 2 theory. So we have another SU2 F flavor symmetry, which gives rise to the fugacity Y. So if we write down the explicit form of the index for vector and hyper, then we just get this formula. So we have this classic exponential, and the exponent is given here. So this is just the character for the adjoint representation of SUN, and we have something in the parentheses. And finally, as usual, we have this Haar measure integration. So this is the Schur index for N equals 4 super Mears. Now let's look at the Schur index of TP, N theory. So before that, we need to know the index, the Schur index of DPSUN, which is the building block of TP, N. So it turns out the Schur index of DPSUN is very simple. So it's just given by the plastic exponential here. So again, we have this adjoint character and with some coefficient here. So in order to give the to obtain the Schur index of TP, N, we can just take the contribution from the vector multiplet and the contribution from the individual building blocks, DPSUN. So we have this kind of formula. So now we can plug in the Schur index of DPSUN into this formula. Then after some manipulation, we can find the Schur index for TP, N theory explicitly. So it's given in the second line here. So we see that this formula is very similar to the Schur index of N equals 4 super Mears theory. So we have the place exponential, we have the adjoint character, and the only difference is just in the parentheses. So in order to actually we can make the connection or relation more precise if we just take the Schur index of n equals 4 SUN superamials by specializing the figurative to some special values. So here we have this figurative q and y. We can just take a q to q to the p's power and y to the q to the p over 2 minus 1. So once you specialize the figurative of n equals 4 SUN superamials to this kind of figurative, then one can easily see that it recovers the Schur index for TP, n theory that I wrote in the second line. So this means that we have a non-trivial index relation relating TP, n theory and n equals 4 SUN superamial theory. And this is a starting point for my discussion in the following. So far, we get the explicit expression for the Schur index, but the problem is that in order to really find the expansion, we need to perform the hard integration. This is very complicated, especially if the rank of gauge group is large. However, in recent years, people have made a lot of progress in deriving the explicit Schur index, and they found many interesting closed form expression for the Schur index. This is something I'm going to do for the TP, n theory today. So for example, almost 10 years ago, this group of people found a closed form expression for the unflavored Schur index of n equals 4 UN superamial theory. So this is the formula. So instead of Harmonic integration, the Schur index is given by some infinite sum here. And this is so in each summand, we have some binomial and also some powers of Q. And there's also a coefficient in front, which is given by the theta function. So we see that this formula is very simple. We can just evaluate this explicitly and get the expansion in Q very easily. However, in this case, we only have one figurative Q, and this is the unflavored Schur index. But for our purpose, we want to know the flavored Schur index in order to obtain the index for TP, n theory. But unfortunately, this has also been done by these two people 2 years ago. So they found a closed form expression for the flavored Schur index of n equals 4 UN superamial theory. So it turns out that it's given by the product of two terms, the lambda here and the Zn here. So lambda is very simple. So we have some powers of C. So C is just related to Y through this very simple formula. And we have some Q POCAM symbols. Zn is defined through some generating function here. So here I introduce another figurative mu, then I consider mu to the n times Zn and then sum over n. So the way that they found this formula is that they have some Fermi-gas formalism. So essentially, n here is just the number of fermions, and a formula like this just gives you a grand canonical partition function in statistical mechanics. And the generation function has a very explicit expression in terms of some infinite product here. So if we consider the expansion in mu and compare the coefficient, then we can easily find the Zn factor here. And furthermore, we see that in lambda, we have this U factor here. And also in Zn, we have this U variable. So the U variable is an auxiliary variable, so it can be arbitrary, but its contribution somehow cancels out finally. So we can just choose any U we want, to simplify the formula. And this is the trick I will use. So now with all the ingredients, I can now try to get a closed form expression for the Schur index of TP, n theory. So there are just 3 steps. First, we just use the index relation that I showed you before, which relates the index of TP, n theory and n equals 4 SUN superamial theory. Then the index for SUN superamials is just given by the UN index divided by U1 index. And finally, we need to choose some special value of U in order to simplify the formula. And this is the most delicate part of this computation. And after some trial and error, I found this formula. So it's given by the Schur index of TP comma n theory is given by the product of two terms, C and C. So C is given here. It's given by some Q to some powers and some Q POCAM symbols. And also this C TP comma n is also defined through some generating function. So we see that the structure is very similar to n equals 4, the Schur index of n equals 4 via Mills. And this is not surprising because the derivation is just using the index relation. So far, this is not so surprising. The surprising thing is that actually we can simplify the formula even further if we focus on the theory we are interested in. So previously, I told you that I studied the series TP comma n, where P is 2, 3, 4, 6, and P and N are co-prime. So if we impose this kind of condition, one can show that actually the C factor can be further simplified. So up to this sign is just given by Q to the minus 1/2 times N squared minus 1 times 1 minus 1 over P. So if you remember the formula about the center charge I told you before, then it's easy to recognize somehow the blue part is exactly the A and C center charge of this family of theory. So in the end, the C factor is just given by Q to the minus 1/2 times the C center charge up to a sign here. And all in all, we can get the final closed form expression for the Schur index of TP comma n theory. So it's given by Q to the minus 1/2 C center charges times this curly C factor. So here I absorb this sign factor into curly C and define this curly C through this kind of generating function. So this kind of sign is actually important, to make sure that we have some, for example, the curly C is start with positive coefficients. So now we get a index which is very simple, and first of all, it shows some factorization behavior. So this is good, but is there any physical meaning associated to this kind of factorization? Yeah, there's another question.
Hi, quick question. So in the paper with Monica and Jaewon earlier, we said that this, in the case of P equals 2, we said that this was actually this quasi-modular function called the McMahon's generalized sum of divisor function. Is this?
Yeah, I will show you later. Yeah.
Oh, this is what this is here. This curly.
Yeah, I can derive that formula from this.
Okay, nice. Thank you.
So in order to understand this kind of factorization, let me first review the famous SCFT VOA correspondence. So according to this group of people more than 10 years ago, they found that there's a nice correspondence between 4D anchor superconformal field theory and the vortex operator algebra. In particular, the vortex operator algebra is independent of the marginal deformation. So if we can find the VOA in the weak coupling, then the same VOA survives in the strong coupling. So this is a very nice feature. And there are many dictionaries relating to the two sides. For example, we can look at the center charges. Then one can show that the 2D center charges of the VOA is given by minus 12 times the 40 C center charges. So because for unitary superconformal field theory in 40, C is always positive. This means the 2D center charge is always negative. This means that the VOA is always non-unitary. This is one relation. And there's also a more non-trivial relation relating the index of 40 angle superconformal field theory and the character of VOA. So before that, let me distinguish two important quantities in this context. So there's a thing called the Schur index that I was talking about, and there's also another quantity called that I will call it as the Schur partition function. So the index I starts with 1 because this just corresponds to the vacuum. There's a unique vacuum in superconformal field theory. But there's also another quantity called the Schur partition function because the index can be computed, for example, using localization. And in this case, just correspond to the superconformal field theory S3 times S1. So from that perspective, the partition function would agree with this index up to some factor, and this factor is called the supersymmetric Casimir energy. So for the Schur index, somehow the supersymmetric Casimir energy is very simple. It's just given by Q to some minus C2D divided by 24. So, and this factor is also very common in 2D rational conformal field theory, for example. So the precise statement between superconformal field theory and the VL is that the Schur partition function is identified with this vacuum character. So Z equals to chi vac. So we need to include this kind of supersymmetric Casimir energy term in order to identify with the vacuum character. So we shouldn't use the Schur index.
A question?
Yeah.
Is this a definition or the
which one is the definition?
I and Z? You have a relation between I and Z with some prefactor. Are these two independent computations, or this is used as a definition of the other? You first compute I and then you define Z like that?
I don't think it's a definition. I mean, for example, the index can be computed by just looking at the individual single letter and then plus exponential stuff. And the partition function, I mean, in general, can be computed from this localization technique. And it can be computed on some general manifolds. In the special case of S3 times S1, so the two are related in a simple way up to some factor, and people have found the difference. So in this case, it's very simple.
How do you show that they are equal to all orders?
I think, for example, in this paper, they prove that somehow this equation holds. And actually, in more general context, not just for Schur index.
They proved it, or this is a physics level? What really was done?
They use some equivalent method to show that the partition function S3 times S1 agree with index up to some factor, and they compute the factor explicitly. And this factor is given here if we consider Schur index and Schur partition function.
So what again is the physical principle? Why there should be equality?
I mean, for example, the index it just counts the local operators, right? So we can, if we use radial condensation, the local operator just corresponds to state on S3. So we can just consider superconformal field theory on S3 times S1. But if we put superconformal field theory on S3 times S1, we can then compute the partition function. So they are supposed to give quantities which is related to index. And this has been shown explicitly. And they found the difference, which is the supersymmetric Casimir energy.
Let's see.
Yeah.
Okay. Thank you.
Yeah. So as I will show you later, the vacuum character enjoys some modular properties. So the Schur partition function should also enjoy some modular properties because of this identification. So previously, I showed you that the Schur index of TP common theory is given by Q to the minus 1/2 times the 40 seasonal charge. If I use the dictionary, then we see that this factor is exactly the supersymmetric Casimir energy term. And the leftover is just the Schur partition function. As a result, the curly C is identified with the vacuum character of the corresponding VLA. So previously, I showed you that this Schur partition function can be defined through some generating function, but it can be also be obtained explicitly by computing the expansion of mu, and then we find this formula. So it's given by n-1 fold of infinite sum. So this looks a little bit complicated. Let's look at a very simple example, namely P equals 2 case. So if P is 2 and n is even, then one can show that actually the curly Z is 0. But if n is odd, then we find that this curly Z is given by AK of Q square. So AKQ is given here, and is known in the literature as Mark-Mahon's generalized sum of divisor function. And this was first observed by Kahn, Rory, and Song. But here I give you a derivation. And furthermore, this formula applies to other p's as well. For example, if we look at the p equals to 3, n equals 2, then we find the Schur partition function is given here. So it's very simple, and this is expansion. And similarly for p equals 4 and n equals to 3. So it's also very explicit. So now I'm going to talk about the modularity. So more precisely, I will show you that the Schur partition function actually satisfies some modular linear differential equation. So let me first introduce the modular linear differential equation in this context. So in general, the modular linear differential equation has this kind of structure. So we have some differential operator, dqk and dqk minus r. And we also have some functions, fr tau. So here, fr tau is just the modular form. So namely, it's a function from the upper half complex plane to the full complex plane. And it transforms in a specific way under SL2Z transformation. For example, under SL2Z transformation, tau would go to A tau plus B divided by C tau plus D. So FR evaluated as this value is just the original FR tau times some factor C tau plus D to the 2r's power. So the 2R here is just the weight of the modular form. And in order to be a modular form, we also need to impose some finiteness condition at infinity. This is not important, so I'm not going to talk about it. So important thing is that somehow the modular form has very rigid structure. So mathematicians have shown that the ring of modular form of SL2Z is freely generated by E4 and E6. So here E4 and E6 are just the Eisenstein series. And this is a general definition for Eisenstein series for E2K. So it's given by some Bernoulli numbers and some infinite sums. So the Eisenstein series E2K is a modular form of weight 2K if K is bigger than 1. So if K is 1, then we get a E2, but this is not a modular form, but a quasi-modular form. Because if we perform a modular transformation, then we would not only get this piece, but also another piece. So because of this property, we can write any modular form as a polynomial of E4 and E6. This means the space of modular form is finite dimensional, and there are only finite coefficients that we need to specify in this polynomial in order to fully determine this modular form. So we just described this modular form FR tau here, but now we would like to discuss this dq. So in general, we have this dqs. So this is a modular differential operator. So it's constructed from ordinary derivative q dq and quasi-modular form E2. And it also transforms very simply. If we perform SL2Z transformation on Q, then we get D gamma Q. And this is just proportional to dq up to the factor C tau plus D to the 2s. So we see that this transformation behavior is very similar to the transformation rule of modular form. So for any positive integer s, we can construct a unique modular differential operator. And now we can just combine the modular forms and the modular differential operators together to get this kind of modular linear differential operator, curly D here. So we just consider all the possibilities and make sure that the weights are the same for each individual term. And if we fix the weight, then the modular linear differential operator is almost completely fixed up to some constant coefficients coming from the freedom in modular form. This is a very rigid structure. So now I'm going to talk about the solutions to MLDE. So In general, the MID has k linearly independent solutions because the curly D, namely the modular linear differential operator, is the degree k differential operator. So we have k solutions. And furthermore, the k solutions also form a vector-valued modular form. This is because if chi tau is a solution to this MLD here, then we can perform S transformation. Then this chi tau becomes chi minus 1 over tau, and Q becomes the Q tilde. Because of the covariance and the SL2Z, this dq tilde is essentially proportional to dq. And therefore, we see that chi minus 1 over tau is also a solution to MLD here. And then we can just write chi minus 1 over tau as a linear combination of chi j tau. And the non-trivial information is encoded in the this kind of matrix. So we can write chi minus 1 over tau equals to Sij times Sj tau sum over j. And this is just gives you the modular S matrix, which is very common in to the rational conformal field theory. So we talk about the structure of modular linear differential equation and also the solutions. But now the question is, what's the origin of MLD? Why do we have MLD? So at a fundamental level, the MLD just comes from the special type of null states in the corresponding vertex operator algebra. So more precisely, if in the VOA we have a null state in this form, then somehow we are guaranteed to have a modular linear differential equation. So the feature for this null state is that we have this -2 to the kth power acting on the vacuum. So -2 is just a Virasoro generator corresponding to the stress tensor. Then we have some other generator A with mode number -h -1 acting on some state phi. So this is a little bit abstract, but we can use the state operator correspondence to transform the null state into a null operator. Then we would get this kind of structure. So t to the k is given by some sum of operators where each operator has at least one derivative, like t d squared t or t dt. But we cannot have t times t because there's no derivative. So this derivative is an important feature for this null operator. So with this kind of null state, we can then insert the zero mode into the torus partition function. And this would give you zero by construction because the state is null. But the powerful thing for this formula is that somehow the left-hand side can be actually computed using the so-called Zu's recursion relation. So roughly speaking, the Zu's recursion relation is given here. So when we insert zero mode of this form into the supertrace, then this gives you two parts. The first part is the zero modes of A and B, and the second part is that we need to increase the mode number -h to -h plus 2k. And this can be done recursively because we can then move B in front of A and then use the commutation relation to simplify this further. And then we would get something which is similar to the left-hand side again. So this gives you the recursive way to compute the left-hand side of this formula. And in the end, we can somehow pull out this kind of zero mode insertion outside of the supertrace, and then we get some differential operator. And the supertrace without any insertion is just a vacuum character. And this means we just get some formula where we have some differential operator acting on some vacuum character, and this is nothing but MLDE. So far the discussion is a little bit abstract. Let's look at a very simple example. The simplest example is the A1, A2 theory. So the VOA for this theory is given by the 2,5 Liang VOA. And famously, there's a null state in this VOA. It's given by A-4 acting vacuum minus fifth thrust A-2 square acting vacuum is 0. So this is a null state. And in terms of operator, it's just given by t squared minus 3/10 d squared t equals to 0. So we can insert the zero mode of this null state into the torus partition function and get a one-point function which is guaranteed to be 0 because the insertion is null. And the left-hand side can then be evaluated through a Schur recursion relation. For example, one can show that L-4 has no contribution because it's a total derivative, and therefore there's no zero mode associated to this L-4. For the L-2 square, if we insert into the supertrace, then we can use the Schur recursion relation. We get two parts essentially. So in the first part, we have the zero mode for a stress tensor, and this one can be obtained by through some differential operation, because we can pull this exponent of Q down by taking derivative with respect to Q, and this corresponds to the dQ2 here. And there's another term which is given by increasing the mode number of -2 to L2, and then we have this E4 outside. And this can also be evaluated if we use the commutation relation. We can move L-2 in front of L2, and L2 would annihilate the vacuum omega. But meanwhile, we also get a non-trivial commutator between L2 and L-2, and that is proportional to the center charge. And therefore, we finally get something here. And this coefficient, 11/5, is just proportional to the center charge of Liang VLA. So if we are careful enough about all the coefficients, we would find this kind of MLD. So that example is very simple. We can also look at another example, which is A2, A3 theory. So in this case, the VLA is given by the W3 algebra with this kind of center charge. So it has two generators, T and W. And there are many null states in this VLA, but one of them is given here. It's a little bit complicated, but the important feature is that almost every term in this operator has at least one derivative, except for the first one. And this is exactly the feature we want. And then we can insert the zero mode of the corresponding null state into torus partition function and get 0. And this can be converted to MLD using Schur recursion relation. So coming back to the theory I'm interested in. So previously I showed you that there's a very simple closed form expression for the Schur partition function. And according to the general discussion I told you just now, this kind of Schur partition function or vacuum character should be annihilated by some modular linear differential operator, curly D here. And the Schur partition function should sit in the vector valued module form, which comes from the solution of this kind of MLD. So the current job is to find this kind of modular linear differential operator, curly D here. Let's look at a very simple example, namely the T3, 2 theory, which is somehow the simplest theory. So for this theory, somehow the chiral algebra is known to be given by the so-called A6 algebra. So it has three strong generators, the stress tensor T, and two fermionic solar primary operators, Busan and psi tilde. So here I give you the OPs. So the stress tensor OP is simple, and the second line just gives you the OP between T and the psi tilde. So this is also this just comes from the condition for primary operator. So 4 just gives you the second dimension. And the most complicated OP is between psi and psi tilde. So this is complicated, but somehow it can be obtained by imposing condition that the OP is associative. So we can, if we impose a condition that every 3 operator has a trivial Jacobi identity up to some null operators, then we would find this kind of OP between psi and psi tilde. So with this explicit OP, we can try to find the null states. There are many null states, and one of them is showing here. So it's very complicated. But again, we can see an important feature that almost every term in this operator has at least one derivative, except for the first one. Therefore, this is exactly the NOR operator we want. We can then insert the corresponding NOR state into the torus partition function and get a one-point function, which is 0. And that can be converted into some modular linear differential equation using Zhu's recursion relation. So here I show you the corresponding MLD in this case. So this MLD has weight 10. So we can also numerically verify this expression because we know the Schur partition function explicitly. And indeed, this is true. And furthermore, there's an important feature here. Somehow there's no constant in this MLD. So in principle, we can have E4 times E6 here, but somehow it's absent. So with this MLD, we can now try to find the solutions. So in order to find the solution, we can use the Frobenius method and make the following kind of answers. So we have some series expansion of in Q, and the leading term is given by Q to the piece. So we can plug in these answers into MLD and then get the expansion in Q. And the leading one has Q to the piece power and with some coefficient. We need to impose the condition that the coefficient is 0. And this gives rise to the so-called initial equation. So in this case, the initial equation is given here. 1 minus 3b squared times b minus 1 times b squared is 0. So obviously, we find the 5 solutions here on the right-hand side, 0, 0, 1/3, 1/3, and 1. However, we see that there are some degeneracy in the solutions. And because of the degeneracy, somehow the answers I made here actually is not valid. We need to generalize the answers by including the logarithmic, by including log Q up to some power. And this is this can be shown using some general theory for differential equation, and it can also be seen from a very simple example of second-order linear differential equation. In any case, I found the 5 solutions here. So these are the expansion in Q. And furthermore, I also found that the solution somehow can be converted into some analytical form. So for example, here I have the first line, chi0 equals 1. This is the solution because there's no constant term in MLD, namely there's no E4 times E6 term. And secondly, chi0 log is given by log Q times 1 plus 6 chi1. And chi1 is just the Schur partition function. And the non-trivial thing is chi1/3. So this is a little bit complicated, but somehow it's given by the so-called Dedekind eta function. So it's just the eta3 tau cube divided by eta tau. And chi1/3 log is just given by chi1/3 times log cube. So here, so these are the 4 set of solutions. And now I can try to understand how do they transform under S and T transformation. So we can organize them in a vector chi0, chi0 log, chi1, chi1/3, chi1/3 log. Then we expect that under S and T transformation, the column vector would be related to the untransformed solution through some S and T matrix. For example, this is the T matrix. So we see that there are diagonal terms, but also off-diagonal terms. And the reason for off-diagonal entry is that if we perform a T transformation, tau goes to tau plus 1, then the log Q would go to log Q plus 2 pi I. And this is responsible for the 2 pi I in the off-diagonal entry. And this is the S transformation. So we get S matrix here. So it's a little bit complicated, but one can verify that S squared is 1 and ST cube is also 1. And from the third law, we can also read that chi1 minus 1 over tau is given by the linear combination of chi0 tau, chi0 log tau, and chi1/3 log tau. So this is for T3, 2 theory. But more generally, if we consider TP, N theory, the story is much more complicated. And one important reason that is we don't know the underlying vertex orbit algebra. Actually, only for T3, 2, we know the VLA. Nevertheless, we know the Schur partition function, and there's an algorithm to find the MLD numerically. And with the MLD, we can then find the initial equation as well as the roots. And this is enough for my purpose of studying the high temperature behavior. So before that, let me give you the reason of trying to understand the high temperature limit. So we know that in 2D CFDs, there's a very famous formula called the Cardy formula, which somehow gives you the high temperature behavior density of states in the high temperature limit. And this is universal because it just comes from the modularity. First of all, in recent years, people have tried to understand the black entropy from the index. And this group of people somehow succeeded in reproducing the black hole entropy from the index in the Cardy limit, just for the n equals 4 SUN super zero. And furthermore, somehow the high temperature limiter is not new. It has been studied by some people in the past, and they even found cause from leading asymptotic behavior for the Schur index in the high temperature limit. So in this limit, the Schur index and the Schur partition function somehow agree up to some exponentially small terms, and the leading asymptotic behavior is given by e to the minus 2 pi over tau times 2 times a minus c. And this formula somehow has been shown to be valid in many examples where a is smaller than c. But it's also violated in a few examples where a is bigger than c. So for the theory I'm interested in today, the two standard charges are the same. So it's natural to ask what's the leading asymptotic behavior for the Schur index and Schur partition function. So again, we can look at the simple theory T3, 2. So as I showed you before, we have this modular S matrix, which enable us to write this Chi1 tau in terms of Chi1 minus 1 over tau, Chi1/3 minus 1 over tau, up to some factors. So now we would like to understand the high temperature limit, namely the limit that tau goes to 0. In this limit, if we perform S transformation, then we would get tau tilde, which goes to infinity. And in this case, it's easy to see that this chi p tau tilde is almost 0 up to exponentially small corrections. Therefore, we can forget about this Chi1 minus 1 over tau and Chi1/3 minus 1 over tau because they are exponentially small. And we are left with the last two terms. So in the end, we find in the high temperature limit, the Schur partition function is given by pi divided by 6 root 3 tau minus 1 over 6 up to some exponentially suppressed corrections. So we see that in the high temperature limit, the index blows up, and which is different from this formula, where if A and C are the same, we would just get a constant term. So this formula is not valid for A equals to C. So this is just a special theory T3, 2. How about the general theory of P, n? Again, we can use modularity. So the essence is very simple. We just relate this Chi1 tau with the Chi J at minus 1 over tau using the S matrix. And in general, one can then argue that from the solution of MLDE, the high temperature limit of Schur partition function is given here. So it's some constant times tau to the 1 minus dj's power times e to the minus 2 pi I bj over tau. So here bj is the minimal root to the initial equation, and the dj is just the degeneracy of the roots bj. So once we know the root structure, namely the minimal root and the degeneracy, we can use this formula to figure out the high temperature behavior. And after studying many examples, I can make the following set of conjectures. The first conjecture says that there's no constant term in the MLD, so chi equals 1 is always a solution to MLD, namely b equals 0 is just a root to initial equation. Furthermore, I conjectured that b equals 0 is actually the minimal root to initial equation. And finally, some of the degeneracy is also conjectured to be given by n. As a result, from this formula, the high temperature asymptotic behavior of a Schur partition function is given by some constant divided by tau to the n-1 power in the limit that tau goes to 0. So this formula can be, this set of conjectures can be tested. For example, for the T3,2 series that I discussed extensively, we know almost everything, then we can show that this is true. Also, for the T2,2k plus 1 series, there's a recursive way to compute the index, and we can figure out the leading asymptotic behavior easily. And there, this conjecture is indeed true. And furthermore, we can figure out the coefficient. For some small values of P and N, I can also study the MLD numerically and find the corresponding initial equation as well as the roots. And using this formula, I can also figure out what's the asymptotic behavior in the high temperature limit. And in all examples I study, all the conjectures are true. And finally, actually, the conjecture 1 and 2 are not can be regarded as the consequences of some knowing conjecture or proposals by Beam and Rastetti. So in this paper, they introduced a notion of 2D effective center charge. And in my notation, this is defined as -24 times minimal root. And they propose that this 2D effective center charge is given by 48 times C minus A. In the theory I'm studying, the two center charges are the same, so this is 0. As a result, we find the minimal root is 0. This is nothing but the conjecture 1 and 2. So finally, let me conclude. So today I show you a very simple closed form expression for the Schur index for family of theory that is denoted as P and N, which is interesting because it has the same N and C center charge and also has some index relation with n equals 4 Spearmire theory. So I studied the modular linear differential equation for some small values of P and N, both analytically and numerically. And using the modularity, I made some conjectures about the high temperature limit of Schur index. And this has been tested in many examples. And there are also some future questions that remains to be understood. For example, can we prove the conjecture about the high temperature asymptotic behavior? And furthermore, now we know we can compute the MLDE using some numerical trick. Can we understand the VLA better? For example, find the VLA for some T(n) theory. And finally, it would be interesting to generalize the index formula to some other A equal to series. For example, can we find some closed form expression for those series? Yeah, I think I will stop here. Thank you.
All right, let's thank Hongliang. Do we have more questions?
Yeah, the theory for any of those theories, is there a Higgs branch?
Yeah. Yeah, for this D4 hat SU 2m plus 1 theory. So the Higgs branch has been studied by this group of people. So they found that the 3D magnetic quiver is given by the rank n SU SO8 instant plus center of mass, which is mirror to this theory. So somehow they, as to my understanding, they found the Higgs branch is given by symmetric product of C2 mod D4.
Mm-hmm. I see.
And for other series, somehow using this type 2P realizations, I can compute the dimension of a Higgs bunch. So which is given here.
Mm-hmm.
Yeah, but for this three series of series, I don't know whether one can figure out what's the Higgs bunch. I mean, in an easier way.
How is n related to k?
Yeah, here. Is essentially n divided by p. I mean, the floor of n divided by p.
I see. Mhm. And you don't expect a symmetric product of Klein singularity?
Yeah, I can make some conjecture like this, but I don't know, I mean, how to prove it or whether they are true. I mean, in general, I can conjecture that is given by symmetric product, the case symmetric product of C2 mod gamma. So gamma is D4, E6, E7, E8.
Mm-hmm. And
Yeah, but
would you, since these are symmetric products, it also suggests a construction in a brane system. So
you mean the theory here, the superconformal physical inequality?
any theory which looks like a symmetric product,
Yeah.
could be represented as a brane system where you take the singularity and you put n objects on it.
Okay.
That's a very simple thing, right? I mean, take a D5 brane on a Klein singularity, take k copies. By space is this symmetric product.
Yeah.
Just because you have n point-like copies of the same transfer space.
Yeah, but this is just your expectation, right? Or you have some concrete idea how to realize this kind of theory using brane system.
But also, you said there's incomplete Higgsing, right? So then,
yeah. Naively,
just
they
more
have no
tricky.
Higgs bunch at all because A and C are the same. So, but they turn out to have non-trivial Higgs bunch given here. I mean, at least the dimension is known from this type to be. And this is just the natural conjecture by generating the case of D4 hat SUN. So
as far as you could tell, these conjectures might be correct, but it's hard to show.
yeah, I don't know what kind of technique can be used to derive or approve this conjecture.
I see. But can you compute the Hilbert series in any of those cases?
Yeah, but because of incomplete Higgsing, I think the computation is not valid in a naive. I mean, if we do things in a naive way. I mean, as I said, we can, for example, obtain this series by considering the gauging of several copies of DPSUN, and we know the Hilbert series of the individual plot, and we can just consider integration. But then that's not right because of the incomplete Higgsing. So that computation is not valid.
Do you know the gauge group which survives the incomplete Higgsing?
I don't know. Is there a way to say it or?
In many cases, yes. I mean, we can look at the details. Let's see.
But it should be some SCFT, right? Probably not a gauge theory.
Yeah, it's a question. I don't know.
Yeah. But it's possible that it's known.
Yeah, maybe.
Good. Do we have more questions for Hongliang? Go on.
If it's a conformal field theory, then which survives, then you should have some signatures like scaling dimensions that may be detected like that.
Do we have more questions for Hongliang? But if not, I would say let's thank him again.
Yeah, thank you.
And we can move off the record.